So let us start with our machine learning models. So first we'll be seeing about linear regression. So linear regression is one of the easiest and most popular machine learning algorithm. So it is a statistical method that will use to predict analysis. Linear regression makes a prediction for continuous real and numeric values, like for example, such as sales, salaries, age, product prices, etc. So let us see basic definition of it. So linear regression algorithm shows a linear relationship between a dependent value and one or more independent values. So basically, linear regression performs the task to predict a dependent value based on independent values. Okay, so it can be more than one value. Since again with respect to the linearity relationship, so it is called as linear regression. Since the linear regression shows a linear relationship, uh, which means it finds how the value of the dependent values change um, according to the value of according to the value of the independent variable. So this regression technique finds a linear relationship between those two. Okay, so hence the name also is linear regression. So basically we have an image over here. So here we can see dots. Blue dots are nothing but our data points, and the red color line, which is like going linearly, is called as line of regression. So basically the linear line of regression, and you can consider on the left, on the y-axis will be dependent variables, on the x-axis it will be independent variables. Okay, so we have independent variables and we have the dependent variable, so hence linear regression will be fine with that. Okay, so how exactly we see this in mathematically? So basically we have a formula. So since we are trying to build a linear relationship between two variables, so we use the formula for a straight line. Okay, I hope everyone knows it. Else, if you don't know the formula for a straight line, that is equal to y is equal to mx plus c. Okay, where m and c are constants. Okay, so what exact kind of constant? Uh, here we have c is equal to theta. You can represent it with respect to theta 1 and theta 2 also. So C or theta 1 over here is intercept. So in the previous image we saw a linear line, right? So there was little few are scaled up, so that's why like the linear line will not be exactly like 45 degrees considering from the axis, but it might be like tilted or going multiple times. So here something like 2x would be like going it will be rising as twice as fast as ln while y is equal to x. So singular, so that will be the intercept. So how exactly it will be going, and theta sorry, that is theta 2. Okay, so that is the m slope, and c theta 1 is the intercept. So intercept again with respect to the line we had seen the points. Okay, so the points were like kind of deviated. It is not at the exact same place, so it's like deviated from the linear line. Okay, so it's not on the line. So this intercept is the reason for that. So it will be like slightly elevated or degraded from the line of regression. So basically here we can consider y as our dependent variables. So that is our target variable, and x as our independent variable. So x will be our predictor variable, and theta 1. So theta 1 is nothing but the intercept of the line. So it gives additional degree of freedom. Okay, so it is like a little deviated, and with respect to theta 2 over here, that is m. So that will be our linear regression coefficient. So that will scale factor for each input values, and also we might have some kind of random errors a bit. Okay, so where we are not over here in the formula. Okay, so how do we update theta 1 and theta 2 values? So again, it is not just like randomly you will go ahead and find the values in one single shot. So it is like kind of iterative process. Okay, so you need to do it repeatedly. So iterative, so to get the best fit line, we need to have with respect to the best values of theta 1 and theta 2. So again, this line is what we are generating. Okay, so all the points which we earlier saw is nothing but the data points, okay, or data set, So for that we need to get the best fit line. Okay, so that will be again affected by the factors theta 1 and theta 2 with respect to the uh, straight line formula, linear line formula. Okay, so here the best fit to find the best fit, we need to have the best theta 1 and theta 2 values. So in order to find this, we need to minimize the cost of minimize the cost function. Okay, so that is like J. The cost function represents the difference value between predicted and actual value. Okay, so basically since the predicted and actual value might have positive and negative values, so iteratively we square the errors to make it positive. Okay, so basically we'll see the formula which will make more sense. So here J is equal to 1 divided by n summation. So in the previous video we had already seen the summation, right? So that is nothing but calculating the sum. So basically here in summation we have a variable. Okay, so variable is I. So I is varying from 1 to n. Okay, so n number of points. So 1 to n. So basically here the summation will be carried out for this I to n terms. So that is 1 to n terms. So n terms will be calculated. So predict of 0th, sorry, the first term, second term up to n term. So predict of I minus yi. So here again, as the difference between them can be actually positive or negative. Okay, so it might be like it is like predicted more or predicted less. Okay, from the actual point. So deviation towards left or towards right, you can consider. So that would be positive and negative. So to ignore that, we'll be taking the square of it. Okay, so it will just go that, and also again we'll be taking square root ultimately. So again that is one particular formula which you can see. So difference between the predicted value minus the actual value. Okay, and we have other ways. Like before that, let us understand how do you understand if the line is the best fit. Okay, so basically theta 1 and theta 2 are randomly selected at first and then optimized using gradient descent at the cost function. Okay, so basically you will be like theta 1 and theta 2 randomly the values are selected more like based on an example. So again after that we will be going with an iterative process. So I told it is like one go we can't predict what exactly would be the value, so hence we'll be going with respect to iteratives. So using the gradient descent on the cost function, so we'll be optimizing with respect to new theta 1 and new theta 2 for a better accuracy, and then now like the cost function will be like getting reduced. Okay. So again at some level or after few iterations, it might reach a saturation level. It is not varying much, but also might not be a saturation level. So there can be a point to where it is satisfactory for us. Okay, so if you are getting some 98% accuracy, though at that scenario you might think, okay, so much of theta value or getting this linear line would be sufficient. Okay, so that is what you will be doing with respect to how we will do. And there is other ways of evaluation. So basically instead of using cost function, we can use mean absolute error. Okay, so the taking the absolute error of the absolute value of the error value. Okay, so as I was telling, we had the line and the data points are deviated, right? So basically the predicted value and the actual value, there will be little deviation. So that is what we'll be finding. So we'll be taking the absolute value itself. So here we are, instead of taking square, like here it is like a mean absolute value error, right? So previously I was telling instead of taking square, what we can do is we can just take the absolute value of yi minus lambda xi. Okay, so it here yi here is nothing but again predicted value, and lambda xi is actually actual value. Okay, so taking absolute value. So basically here absolute value means even if it is negative inside the brackets, we will be ignoring it. So no other change. We don't have a square, and we have an absolute value. So basically here again we are avoiding the negative values. So again it remains same. Add everything throughout and divided by n. Okay, so that is nothing but our mean, right? So mean absolute square. And next we have mean squared error can be difficult to interpret at times. So that's why we when we have dealing with large values, we'll take the root of the same. We'll take the root of the same, so which will give us better understanding. Okay, so we will take the square and then root of it. Okay, so basically this is the formula 1 divided by n. So basically summation of e square et. So et would be our error, okay, error margin. So just take the square and then the whole root, okay. So that is what we are doing it over here. So again, with respect to all three formulas, they are actually kind of very close by, okay. So the predictions would also be very close by. So these are the other two formulas which we'll be calculating. Again, if we are dealing with linear regression in our projects, so this will be using a special uh, library known as scalar, which will be providing us the linear regression itself. So directly you can just use the linear regression methods to use that. Okay, so again, we'll leave that to the project phase. So theoretically, this is what linear regression means. I think the uh, concept is very straightforward, and it is the most simplest one. Okay, so any training model, if you are a beginner, you can try out a linear regression. uh, Again, provided it should be supervised learning. Maybe this should have been fitted in the next slide. Okay. So in R square, we first see what is the variation of the error term. So basically how much it is deviated when we fit a line to the mean of the distribution. Then we fit our line and see how much variation was explained by the new fit line. Okay. So like we'll be having one particular line, we fit a line. So then we'll find R square, again iterative process. Then we fit our new line and see how much it is variation like with respect to the new line. So higher the variation explained, the better it is. So if the variation is more, then the line is better. So the value is always like from 0 to 1. So that is like kind of in terms of percentage. And adjusted R square is modified version of R square. Okay, so you have another version known as one was R square, and this is adjusted R square. Okay, so it is like a little modified version of R square. So that has been adjusted for the square, sorry, adjusted for the number of predictors in the model. Okay, so the adjusted R square increases with the new terms improve the model more than it would be expected by chance. Okay, so it decreases when a predictor improves the model by less than expected. Okay, so typically the adjusted R square is positive. It is always lower than the R squared value. Okay, so we'll see the formulas. Okay, so basically R square is nothing but variation of mean minus variation of the line divided by variation of the mean. Okay, so this is what is R square. And adjusted R square, here we have summation of x and y. Okay, so x and y minus summation, individual summation of x, summation of y divided by whole root of n, capital N, into again summation of square, summation of x square minus summation of x the whole square multiplied with n into summation of y square minus summation of y the whole square. Again, this denominator is taken root. Okay, so this is the other formula which you can just apply and find out the linear regression. So next we'll be seeing an example. So we'll just consider basic direct value. So consider the mean variation as 32 and line variation as 6. So here R square would be nothing but variation of mean minus variation of line divided by variation of mean. So that will be 36 minus 6 divided by 32. So basically it is R square. Okay, so it's not R2, R square. So 26 by 32. So we have 0.8125. Okay, so that is a pretty good accuracy. So that means the line explains 81.25 of the variance. Okay, so okay, from that time I'm telling variation instead of the actual word is variation. So even the words are almost one in the same, but it's not variation of mean, it's variance of mean and variance of line divided by variance of mean. Okay, so 81% of the variance. So the remaining is considered to be error, and which cannot be explained. Okay, so basically it is like the deviation, how much is the variation with respect to the line. Okay, so this is the accuracy score what we can get. Okay, so we have few assumptions to linear regression. Okay, so basically linear, first one is linear relationship. We have assumptions for linear regression. So first is linear relationship. So there exists a linear relationship between an independent variable x and the dependent variable y. So based on this assumption only we were able to calculate. Okay, so even all the previous formulas, everything what we have seen, the ways of calculating a linear regression. So the first is again with respect to linear relationship. So second is independence. So the residual are independent. So in particular, there is no correlation between the consecutive residuals in the time series. So basically, individual are independent. Okay, so they are not dependent on each other with respect to the different consecutive residuals, and those are nothing but the different data. Okay, so the next if you are considering data to be in terms of comma separated values, a table probably, so all the rows will be should be independent of each other. Okay, so that is what is meant over here. And next is homoscedasticity. Okay, so kind of little tongue twister over there. Okay, so the residuals have a constant variance at each level of x. Okay, so this is with respect to individual, else it will be hetero. And finally, normality. So the residuals of the models are normally distributed. Okay, so again, that is the normality over here. If one or more of these assumptions are violated, then the results of our linear regression may be unreliable or misleading. So, okay, so this are the limitations. Basically, these are the assumptions where the data set must have, so that we can easily apply our logistic regression. Else, our linear regression. Okay, so if one of them are violated, so definitely we won't be getting much accuracy in the end result. So that's why like this is the criteria of choosing linear regression. So if any one of these is not satisfied, then we can just go ahead with any other model. Okay, so we'll be learning about more models in the next videos. And again, similar to linear regression, we have multilinear regression. So basically, here we are seeing only one particular line. So that is one dimension. So a 2D line in a 3D plane. Okay, so this is where we can have multilinear regression. So as the dimension increases, again, it increases the dimensions of the lines also. So here we are just considering the 2D plane in 3D plane. We can't represent a 3D in 4D. Okay, so so that's why we are going with just 2D with 3D. So to take into account that all the dependent and independent variables, the lines need to become a plane. Okay, so it is like in a plane. So I think this would be the formula. Again, it is pretty similar to what we had seen with respect to a single line regression. So multi-linear regression, single just basic linear regression, and basic multilinear regression is nothing but like y will be our dependent one, and whereas x1, x2 up to xn will be our independent variables. Okay, so that is what I had mentioned in the previous in the starting of the video also with respect to linear regression. So there can be one or more independent variables. Okay, so this might be a slight representation. So we have a three-dimensional figure and we have a 2D plane. Okay, so this is the multilinear regression. Again, I think this is the basic general formula. So if you want to compute again multi-regression, so directly with the help of packages, libraries, we'll be implementing. So I think it is audible. Okay, so we'll not deep down. We'll not dive deep into the again formulas with respect to multilinear regression. So I think conceptually everyone has understood with respect to what is linear regression and how is the extension concept of the multilinear regression. So again, this is not limited to 2D and 3D, so it can go up to 4D, 5D and all. But again, accuracy score over there, the complexity of the data is quite high, so linear regression might not be the best fit model. Okay, so again, that would be given with respect to the data set and the experience what we gain. Okay, so that's all about linear regression.